Yes, so my name's Bea and I'm a postdoc at the University of Oxford, and I'm working on FSS, which is the Farside Seismic Suite. What we'll do is we'll send an instrument to far side of the moon to measure seismic activity. And also it's part of the CLIPS mission as well, so NASA's CLIPS missions. So we all know of the Apollo missions. So the Apollo missions from 11 to 17 all helped scientists answer all the key questions that they had about the field of seismology. And in fact, Apollo 12, 14, 15, 16, and 17 all had seismometers as part of their scientific equipment. So FSS will actually be like NASA's first mission to the far side of the moon, and it will be deployed in the Schrödinger Basin on the south side of the moon. Before I go into FSS, a bit about lunar seismology. So lunar seismology is very different to Earth seismology due to the absence of tectonic plates. The strongest seismic activity on the moon is in fact weaker than the Earth's weakest earthquakes. So we really need sensitive equipment in order to measure it, basically. So some of the key questions that FSS will answer is seismicity different on the far side? How do impact processes shape the lunar crust inside and outside the Schrödinger crater? What is the current micrometeorite impact rate driving seismic hum? So this image shows inside the square, you've got the near side with all the locations of the deep moonquakes, as well as the shallow moonquakes. And outside the square, you've got very few known locations of the moonquakes. So FSS will help in answering a few of these questions. So the core concepts, FSS will be packaged as a self-sufficient payload. So what this means is that it will be independent to the lander, have its own power, communications, and thermal control, and outlive its lander and survive the 2-week-long lunar nights and days. So a bit about the mission. The Farside Seismic Suite, FSS, will deliver 2 seismometers. One of them is the vertical very broadband seismometer contributed by the French Space Agency, CNES, and it is the most sensitive flight-ready seismometer ever built. The short period sensor is the most sensitive and mature compact triaxial sensor available for space applications, and it will be delivered by Kinemetrics in collaboration with the University of Oxford and Imperial College London. So Imperial College London actually make us the sensors, so that's the easy bit. And then we do the testing, the electronics, build the instrument, and then deliver it to JPL. So this image basically shows the lander, which will be provided and made by a company in the US called Draper. And then this diagram here shows the VBB seismometer and then also the SP seismometer tucked in. So we work on the SP seismometer, and that's based on the InSight heritage. For those of you who don't know, InSight was a mission that launched in 2018 and was very successful in collecting seismic data, but on the moon, on Mars, and now we're basically doing the same thing on the far side of the moon. So this is one of the images of a sensor. It's a micro-machine silicon system. And we'll have 3 of these in what we call a Galperin configuration, which is this below, rather than have 1 vertical and 2 horizontal sensors that InSight basically did. And also the spring will be adjusted to account for the lunar gravity. So yeah, so a couple of the key differences between Mars and the moon. This image basically shows FSS at the moment. So it's very nearly completed. So I thought I'd put in these images. However, it's not 100% yet. Like, for example, this is the lid that will go on. However, it won't be this one. This is just a 3D printed one. and it will actually be a transparent one, so you can actually see the inner beauty of it. So yeah, environmental testing is really important for instruments. So our goal was to adapt like the Martian design of the sensor and make it operate on the moon, which is an airless body which has a gravitational field strength of just 1.6 newtons per kilogram. So all these tests are needed to carry out so it can survive launch, the landing, and all the harsh conditions. So that includes tests like shock testing, vibration testing, TVAC testing, which means you place it in a high vacuum chamber and subject it to harsh conditions. So like temperatures of like 200 degrees Celsius down to minus 100 degrees Celsius, and then alternate. So you're subjecting it to harsh conditions, basically. However, there's a couple of tests that are specific to FSS, and that's push testing and noise testing, which I'll go further into in the next couple of slides. So push testing is one of the tests that I did, which is basically a strength test, which was done, if I go back to this slide, which was done on this DT strip, which is the strip in the middle here. So we used this pull tester in the lab to basically exert a force onto this DT strip to see how much force it could exert. And the requirement was that it could withstand at least 30 newtons. And all of our test pieces did, so that's good. So yeah, so we basically exerted a force until the DT strip popped out or the sensor frame broke one of them. And you can see from this plot that it has withstood like 30 newtons, over 30 newtons, so that's good. Also, another test that we did was noise testing to basically check the performance of the sensor. So this is a typical plot that you have of a noise plot. And what this shows is you've got the green line, which is the threshold that we need to be below. And then the predicted is what we thought we'd get from like the InSight sensors. However, like if you look from this region here, from 10 to the -1 to the 10 to the 0, you can see that we're much better than this, which is good. Also, this peak is here because we had a reference sensor that was connected up to it as well, just acted like a reference. If that wasn't there, then this peak wouldn't be there, basically. And then these other tests are there just to see the coherence and the things like transfer function as well. I would have liked to put in a bit more of the testing, such as like the shock testing, vibration testing, and the TVAC testing, but we just don't have the instrument 100% ready. So when I'm actually going back after the conference, I'll actually be doing these tests. So if anyone's going to the AOGS conference in late July in 2023, then hopefully I can update this and talk a bit more about those tests. Yeah, so just a quick summary. So FSS will outlive the Draper lander. It will deliver key lunar science for the far side of the moon, also address key questions that we have relating to the seismicity rate, deep lunar structure, the local structure at the Schrödinger crater, and micrometeorite impact rates. And then also the innovative thermal design allows continuous operation through the lunar night. And then crucial testing is being carried out, and we hope to deliver to JPL very soon, maybe next month or the month afterwards. So yeah, thank you. And this is the team in Oxford, and we've got these two, Tris and Catherine, in the crowd there as well. And then here's my email address if anyone wants to ask me anything or get in touch. So yeah, thank you very much.